In this video, we're going to talk about inverse functions. Now, we'll have to make a distinction between inverses, which may or may not be functions, and inverse functions, which are inverses and also functions. They're not always the same thing. First, we're going to cover some of the content material, and then we'll take a look at some of the homework problems. Let's get to the content first. Let me share my screen. The first thing that we want to think about is what is an inverse and what does an inverse do exactly? When we talk about inverses, we're talking about functions or equations rather that undo each other. These are equations that undo the process of another equation or the processes, whether it's multiplication, division, addition, subtraction, whatever it may be, raising to a power or having a root. They're not always functions. When they are functions, we call them inverse functions. When we call them inverse functions, we have notation that goes with it. When they are functions, we use this special notation. Let's talk about what that notation is. The function, original function, might be f of x. So, given f of x, the inverse function to it, and again, it has to be both the inverse and a function, is written with the notation f with a -1 in the power position, and then of x. This is really a bad idea, whoever came up with it first, because we're used to thinking of negative exponents as being the reciprocal. That is not what we mean here. This does not equal 1 divided by f of x. Instead, this is notation for the inverse function of f, which is also a function. Now, because it's a function, it passes both the vertical and the horizontal line test. In general, the inverse passes the horizontal line test, and then it passes the vertical because it's a function. The horizontal line test is what we use on the original function to determine whether or not the inverse is a function. If the original function passes the horizontal line test, then the inverse equation is also a function. If it does not pass the horizontal line test, it still has an inverse equation. It's just not a function. When we think about these, we often call the ones where the function is, the original is a function and the inverse is a function, we have a special name for them. We use 1-1 as the symbol to represent that this is a 1-to-1 function. Now, what do we mean by a 1-to-1 function? We mean every x has one y and every y has exactly one x. That's what we mean. That both the x coordinates and the y coordinates only get used one time. This is why it passes the vertical line test and the horizontal line test. Let's now move on and talk about something slightly different. What do we do in order to find the inverse of a function? Let's now talk about finding the inverse of a function. We'll call this finding the inverse equation of a function because we don't know whether or not it will be a function itself. We'll start with something that is in fact a 1-to-1 function, and then we'll move on to something that is not. On the first function, I want us to consider the function f of x equal to x cubed. In order to find the inverse equation to a function, we first take the f of x and we replace it with y. This just replaces the notation with y in order to give us something where we can swap the variables. The next thing we do is we label that it's inverse and we swap the variables. In other words, literally switching the x and the y variables. To get the inverse. The next thing we do is solve for y. In this case, in order to solve for y, we need to undo the cube power, and that means take the cube root. When we take the cube root, it's an odd root, which means we do not need a plus or minus. The cube root undoes the third power and lifts off and gives us just the y, which is underneath. Now we need to determine if it is in fact an inverse function. Check the original to see if it passes the horizontal line test. That means we need a graph. Now we can either graph it by hand or we can use a graphing utility such as Desmos. X cubed is one of our toolkit functions, so you should know what it looks like. Again, it comes up, flattens out near the origin, and then goes up very steeply again. It has the points -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8 on the graph. As one of our toolkit functions, you should have already memorized what this looks like. When we're looking at this one, we know it passes the vertical line test because it is a function. Now we want to know, does it pass the horizontal line test? In other words, does every y value only get used once as well? The reason is when we swap the x and y, what used to be an x is now a y, and what used to be a y is now an x. We need to know if the new function with its x's, which are the old y's, if they only get used one time. We draw a series of horizontal lines to determine whether or not it passes the horizontal line test. Does it ever cross the graph more than one time? No. That means that it passes the horizontal line test. And because it passes the horizontal line test, the inverse is a function. Since the inverse is a function, we can use function notation. Then we'll take the f of x that we had originally, and we'll represent the inverse function by putting the -1 in the power position, although it does not represent the reciprocal function. And we set it equal to the new function we found, which is the cube root of x. This means that f and f inverse undo each other. Let's write f down below it so that we can see the two of them side by side. Can you see that in fact they do undo each other? What does f do? It cubes things, takes them to the third power. And what does f inverse do? It undoes the cube root. In other words, they each undo each other. When we graph these two functions, they make a mirror image across the identity function, which is its own inverse. Now, why would the identity function be its own inverse? Think about the identity function. Remember that this is the graph of y equal x, which cuts quadrants 1 and 3 in half. This is the line at a 45-degree angle. If we were to take this graph and swap so that we could solve for the inverse, what would we get? Again, we get exactly the same equation, just in the reverse order, x equal y instead of y equal x. But we know that y equal x is a function because it's a slanted line. Therefore, the identity function is its own inverse. When you have a function and its inverse, they make a mirror image across this unique line that is its own inverse in 3 different ways: graphically, algebraically, and point to point. Let me show you what I mean by graphing x cubed and its inverse in Desmos. First, we'll graph the original function y equal x cubed. We'll have to lift this up a little bit so that we can see the graph. If we want to see the points at 2, 8, and 2, -8, we'd have to scroll in more, but then we lose some of the detail of the function. Let's graph the inverse, which is y equal the cube root of 8. Now, how can we enter a cube root? We can do the 1/3 power, which gives us the same representation as the cube root. Or we can click here and we can click on this menu down below, y equals, and then we click on the menu and we come until we find what we're looking for. There may be more functions here if we click on functions. Scrolling down, I'm looking for something that gives me the ability to do radicals. Unfortunately, I'm not finding any. I was hoping, there it is, right at the bottom. It's under number theory. I can click on the one that has an n in the index position of the radical. And then it's clicking and it's blinking up here where the index goes. I put 3 for that, and then I hit the tab key and I say x. You can either do it as x to the 1/3 power, or you can click on functions and scroll to the bottom to find a template. Look at these 2 graphs. They're not symmetric with respect to the y-axis when you fold on the y, and they're not symmetric with respect to the x-axis when you fold on the x. But there is a kind of symmetry here. Do you see it? When we're looking at these, there is a way that they fold together and touch, and that's across the identity function. Remember that the identity function is y equal x. Let's put it on here and make it a dashed line so that it is not part of our graph. Do you see that if we were to fold along the identity function, these 2 functions would in fact lay on top of each other? That means that they're inverses. This part of the cube root function lays on this part of the cube function. And this part of the cube root function lays on this part of the cube function. This part of the cube root function lays on this part of the cube function. In this way, they are mirror images, but across the identity function y equal x. This is always true for an inverse equation and the original function. Whether the inverse is a function or not, they do form mirror images across this line. Let's go back to our notes now. What's another way that we can determine whether or not 2 graphs are in fact inverses? Suppose I had given you the equations to start. Suppose that I had said f of x is equal to x cubed, and g of x is equal to the cube root of x. And I didn't tell you that they were inverse functions of one another. I asked you to find it algebraically by taking the composition of one function with the other and then reversing the process in the order. In other words, if I can show that f composed with g using x is equal to x, which is equal to g composed with f using x, then I will have shown that they are inverse functions of one another. This kind of composition is in both directions, so we have to check them both. Checking one direction doesn't prove it. It may work in one direction, but not in the other. So you have to check both directions. Why would we get x back again? Because both functions start with x as the variable. And what does f do to it? It cubes it. Then g comes along and uncubes it, so you get back to x. What does g do? It takes the cube root. Then f comes along and cubes the cube root, so you get back to x again. Let me show you what I mean. Remember that f composed with g can also be written in the notation where f is on the outside and g of x is on the inside. This means that I'm going to write the f function with empty parentheses, and I'm going to substitute the g function inside of it. Notice that the cube root of x cubed would in fact give me x. Again, that proves that f undoes g, the outside undoes the inside, but does not prove that g is capable of undoing f. Let's now prove that g can undo f by finding g composed with f. Now we write the g function, which is the cube root of something, and we substitute the f function in place of the empty parentheses. The f function is x cubed. Because it is an odd radical, and that means that we will not have a plus or minus. We get into trouble with the even ones because of the plus or minus. We'll do one of those next. When I take the cube root of x cubed, it lifts off the cube, and again, I get back to x. Because both directions give me x, I know that they are not only inverses of one another, but inverse functions. They are one-to-one functions. It works in both directions. That means that I can say G is F inverse of X, and I can say that F is G inverse of X. In other words, they're each other's inverse. It works both directions. Let's work one that does not show that they are both inverses of each other. Let's take a look at the function f of x equal to x squared and g of x, which is equal to the positive square root of x. You might think that these should be inverse functions, and one direction will work, but the other direction does not work, and we need to know why. Let's take a look at these two, doing it algebraically, then we'll graph them, and I'll show you why they're not inverse functions of one another and not inverse equations either. When I do the f composed with g to test for inverse functions that are one-to-one, I'm going to write f on the outside, which gives me something squared, and then I substitute the square root of x inside of it. When I square a radical, it does lift off the radical and gives me what's underneath it, which gives me x. This direction does seem to work. F does undo g. Then it must be g undoing f that's a problem. G is the square root of x. We replace the x with an empty set of parentheses and substitute x squared inside. Now, this is a definition you may not have heard before and may be new material for you. Note that the square root of something squared is not the something. It's the absolute value of the something. Why does it have to be the absolute value? The reason is there's no sign in front of the square root, so we must force the value to be positive by putting it in absolute values. But we don't know if x is positive or negative. So just dropping them would not be accurate. Now let's take a look over here at the graphs. Because these two did not both give us x, we know that they're not inverse equations of each other. Let's graph them and see what we get. We'll change the first one to x squared, and we'll change the second one to the square root of x. Do you see what's happening now and what the problem is? The problem is that while this part of the square root function undoes this part, and this part of the square root function undoes this part, there's nothing for the left side of the parabola to lay on top of. These are not inverse equations of each other. They are both functions, but they're not one-to-one. Notice that x squared flunks the horizontal line test. Its inverse is not a function. What is the inverse of x squared then? Let's find the inverse of x squared. Because it's not one-to-one, it flunks the horizontal line test. We're looking for the inverse equation to f of x equal x squared. Remember the steps. We start here and we replace f of x with y. That gives us y equals x squared. Then we swap the variables and label it the inverse. This is the inverse equation, not the inverse function. I get x equals y squared. Finally, the last step is to solve for y. Because I have y squared, I need to take the square root of both sides. But when I put in a square root or any other even root, I have to put in a plus or minus. This happens on the side without the square, which gives me not just the square root of x, but also the negative square root of x. This means that the inverse equation to x squared is plus or minus square root of x. In other words, it's both the upper arm and the lower arm. Because this is not a function, it won't pass the vertical line test. I am not allowed to use the notation. Since it's not a function. Let's take a look over here and I'll add in the plus or minus. I think if I put in a plus followed by a minus, it will go to plus or minus. No, it didn't. Let's see if there's a plus or minus included in one of the templates in the keyboard down below. If I click on functions, I think it might be in the same place again, down towards the bottom. So I'm going to scroll rather quickly through the rest. I don't see a plus or minus, which means Desmos doesn't have the ability to do that. What I can do, though, is I can go ahead and enter the other part separately as y equal negative square root of x. Now I have them both graphed, and I'll turn both colors blue to indicate that they're coming from the same graph. Now you can see that the inverse equation to an upward opening parabola is a right opening parabola. The problem is the original function flunks the horizontal line test, which means that the inverse equation flunks the vertical line test. It's not a function. Is it an inverse? Yes, but not an inverse function. Most of the time, we are interested in inverse functions, and that's what we'll focus on most of the time. They still make a mirror image of each other across the identity function y equal x. Let's see some other characteristics of inverse functions. Let's find a spot where it goes through exactly. We have the point 1, 1. We also have the point 2, 4. Let's show where the point 2, 4 is on the graph. 2, 4 is on the right arm of the upward opening parabola. Right arm goes to the right from the vertex, and the left arm goes to the left from the vertex. It's on the right arm. When you're looking at this, where did this exact point go on the inverse function? Well, think about what you did when you were solving for it. You swapped the x and the y. So that must mean that when I swap the coordinates in the ordered pairs, I get the point on the inverse. Can you see that these 2 points here would lay one on top of the other if I were to fold on the dotted green line, which represents the identity function? In other words, the point on either graph and the point with the coordinates reversed meet together when you fold it on this line. This is true of all points on the graph. So there are 3 ways that you can be an inverse. That's point to point, going by ordered pairs, by swapping the x and y equation and doing it algebraically, and also by graphing and showing that you're a mirror image across that line. Now, there are some graphs besides the identity function that produce the same equation when you look for the inverse equation. Let me show you an example of one. Let's look at the function f of x equal to 1 over x, the basic rational function. We're going to graph it on our graph over here and take x squared off. When I enter 1 divided by x, I can see the equation that I've got here. Now, I don't know what the inverse is, so I've left that part blank for now. Looking at the graph, I also need to take off these ordered pairs, or at least turn off the color by clicking on the circle with the color in it. Now, when I'm looking at each of these, notice that it is going to have some symmetry, except I don't have the inverse on here yet. How could it already be symmetric to the identity function if the inverse isn't on here? Well, the only way that could happen is if it's its own inverse. Let's see how that works. Remember what the rules are. First, replace f of x with y. Then we have y equal 1 over x. Then swap x and y and label. Now we have an inverse equation, which we don't know yet whether or not it's a function. The inverse equation is going to be x equal 1 divided by y. Now we can look up here at the original. Let's take a look at our graph again and see if it passes the horizontal line test so that we know whether or not the inverse equation is also a function. While this does look like it becomes horizontal, it's actually getting closer and closer to the axis as it goes further and further to the left. It does pass the horizontal line test at all points from here up to here. That means that it is a one-to-one function, and its inverse is also a function. Since the inverse is a function, then I should solve for y and replace the y with inverse function notation. So the next thing I did was check the horizontal line test. The original function, f of x equal 1 over x, passes it. So that means it's a one-to-one function, and the inverse is a function too. What we do next is we need to take this equation and solve for y. When we solve for y, we can go ahead and write both sides of the equation in fraction form. That means instead of x by itself, we write x over 1 equals 1 divided by y. Again, we have one fraction on the left and one fraction on the right, so we can cross multiply. When we cross multiply, we get the numerator on the left times the denominator on the right. Then we get the denominator on the left times the numerator on the right. This gives us xy equal to 1 times 1, or xy equal to 1. The next thing we need to do is to continue to solve for y. After we've cross multiplied and simplified, then we're ready to solve for y again. This means that I need to isolate y by removing the x multiplied by it by dividing it. This gives me y equals 1 over x. But that's what I started with, which is what I pointed out when we looked at the graph. The graph of the original by itself already forms a mirror image across the identity function, which must mean it is its own inverse. And that is true. When I swap the x and y, I get the same equation algebraically as well. So graphically, it is its own inverse, and algebraically, it is its own inverse. What about swapping ordered pairs? Let's check a couple of ordered pairs. Looking at the original function, let's suppose we let x be 2. Then 1 divided by 2 would be the number 1/2. So 1/2 should be on the graph of the original. There it is right there. Now, if I were to swap the coordinates, I would not have the same point. I would have a different point. Swapping the coordinates would give me 1/2 and then the 2. Do you see that these two ordered pairs will lay on top of each other when I fold it along the identity function, but they're not identical to each other. Because they're not identical to each other, it's not exactly its own inverse when swapping point to point. The only function that is its own inverse all three ways is the identity function, and that's why it got named identity. Whether you're looking at it by the graph, swapping ordered pairs, or solving algebraically, the identity function gives you back exactly itself. Now let's take a look at some of the homework problems. In problem number 1, we're told that f of x is equal to -6x plus 8, which we know is a slanted line. Because it is passing the vertical line test, we know it's a function. Plus, they use function notation, which they cannot do if it does not pass the vertical line test. If you imagine a slanted line, though, you know it must also pass the horizontal line test, which tells you that all slanted lines are also one-to-one functions. That means the inverse equation is also a function. So we can use inverse function notation. In this problem, it asks us to find that inverse equation that's also a function. Let's write down the function to start with. We have f of x equal to -6 plus 8. Now we want to find the inverse function. First, we replace the notation with y. This gives us y equals -6x plus 8. Then we swap x and y and we label it the inverse. The reason I suggest that you label it the inverse is, believe it or not, on exams, I have had students swap, forget they swapped, and swap back. What happens if you swap twice? You end up where you started, of course. So now I have students label that line where they swap the variables so they know not to swap again. I know you're laughing at home, but I've seen it happen multiple times. You get nervous on exams, right? And you make silly mistakes like that. It happens to everybody, not just you. I've made my own share of silly mistakes. When we swap the x and y, we replace each x with y and each y with x. We know that this one passes the horizontal line test. So the inverse is a function. So we want to solve for y and replace it with inverse function notation. So our next step is to solve for y. To solve for y, we're first going to isolate the y term. To isolate the y term, I'm going to subtract 8 from both sides of the equal sign. This keeps the solutions unchanged. Then to isolate y itself, I'm going to divide both sides of the equation by -6. I can also divide each term by -6, which is actually my preferred way of doing it. I write it in this form first because I want to point something out when we reach the final conclusion. But keep in mind that it is also okay to split it into two fractions. X divided by 6 minus 8 divided by 6. When I look at this one, I know that it is a function, so I replace the y with the function notation for the inverse function, f inverse of x. We only want to use that notation if the inverse equation is a function. That means the original has to pass the horizontal line test. But we thought about a slanted line, and we knew a slanted line would pass a horizontal line test at every point. So we know that it is a one-to-one function, and its inverse equation is also a function. Now, why did I want to write this one here? Let's write f of x below it and think about what the process is. Let's think about what f does to a value x. First, it multiplies it by -6. Then it adds 8. What about the inverse? What steps does the inverse take? When I look at the inverse, notice here that the inverse first subtracts 8. And then it divides by 6. That's why I kept it in that notation, so that I could point out that these two processes are exactly inverses of each other. They undo each other. That's what an inverse does. It undoes the processes of the other equation. First multiply by 6, then add 8. Let's undo it. Subtract the 8, then divide by this -6. I lost my negative. That's a good catch. All right. Does everybody understand now why these are inverses of one another? Do you see how they undo each other's process? I could have started with the inverse and said it subtracts 8, then divides by -6. How do you undo that? Go in the reverse order and undo each step. Multiply by -6 and then add 8. That undoes what the inverse function does. Let's move on to the next equation. In the next equation, we have a fraction, and we're again told to find f inverse of x. The fact that they're telling us to find f inverse indicates that the original function must pass the horizontal line test. We have not studied this type of function yet. It's called a rational function. We will be studying it later in chapter 5. But until then, let's graph it on Desmos to make sure that it does pass the horizontal line test. We have 7x over x plus 6. Now let's look at our graph. I'm going to scroll out some so that we can see the full thing. Aha! I knew there was another piece because I already know what a rational function basically looks like. Two boomerangs in opposite quadrants. So I knew there was another piece. We haven't studied them yet, so don't worry if you didn't know that. I wouldn't expect you to. Now, what do we have when we look at this graph? Does it pass the horizontal line test? Yes, this is getting lower, but it continues to get lower the further out we go. It never becomes truly horizontal. And that means that it will pass a horizontal line test. The same is true in this direction. It's getting higher, but it never goes fully horizontal. So it does pass the horizontal line test. That means it's a one-to-one function, since it also passes the vertical line test. And every x gets used exactly once, and every y gets used exactly once. Now let's look back at the problem that we have to solve. On this problem, we are looking for f inverse of x. We're given that f of x is equal to 7x divided by x plus 6. Again, we replace the notation with y. That gives us y equal 7x divided by x plus 6. The next thing we do is we want to swap the x and y variables and label it. Again, you'd think I'm crazy, but I can tell you I've seen it so many times. Students swap, get agitated, and swap again. And then they want to tell me that the inverse is the function itself, which would not be correct in most functions. So we label it. This is the inverse. That's code for don't swap again. Where the y was, we put x, and everywhere there was an x, we'll put a y instead. Now we know it is a one-to-one function, so it passes the horizontal line test, and that means the inverse is a function. So we need to solve for y and replace it with function notation for the inverse. The first thing we need to do is get rid of the fractions. Since we only have one fraction on the left and one fraction on the right, we're going to write it as a fraction on both sides and then cross multiply. When we cross multiply, we get the numerator of one side times the denominator of the other side set equal to each other. Then we'll go ahead and multiply it out and simplify if there's anything that will simplify. This gives me x times y plus 6x. Remember to distribute the x over both terms inside. There's only one term inside, and 1 times 7y gives me 7y. Now I need to isolate the y terms. I have one on the left and one on the right. That's not going to work. I need to get them together. I'm going to do that by subtracting the 7y, but it really doesn't matter which one you move. To isolate, I need to move any term that does not have y to the other side of the equation. That means the plus 6x needs to move to the right by subtracting 6x from both sides. Notice that where the equals is, I have the same thing written on both sides, keeping the equation balanced and the solutions unchanged. This gives me xy minus 7y equal to negative 6x. Now that I've isolated the y terms, I want to factor out y. I am not looking for the greatest common factor. I'm only looking for the factor y. I'm trying to isolate y by itself, not a greatest common factor. Now I take y out by dividing it from each term on the left-hand side. When I take y and divide it from xy, I get x left behind. When I take negative 7y and divide by y, I get negative 7 left behind. After I've factored the y out, then I want to divide by the binomial factor, the group factor, x minus 7. This is going to let me isolate y on one side by itself. When I simplify to get to the next step, I have simply that y is equal to negative 6x divided by x minus 7. Now, because I know that the original was 1-to-1, I can replace the y with inverse function notation. Come over here, make sure you know what the name is. If the name is g, it should be g inverse. If the name is f, it should be f inverse. We replace the name since it is a 1-to-1 function. So the inverse is a function. That is the answer to this particular problem. When entering it in, you need to be careful and make sure you put parentheses around the group factor x minus 7 in the denominator. Let's practice that. The negative 6x in the numerator, you could put them in, but you don't have to put parentheses in because the order of operations will do the multiplication from left to right, followed by the division. That's the order of operations, multiplication and division at the same level, whichever you hit first as you go left to right. So it multiplies negative 6 by x, and then it divides by what follows. What follows needs to be the entire group, x minus 7. Check your answer to make sure that that's what you have on the other sheet. Then check your answers and check the preview to make sure the preview matches what you believed it should be. If your preview matches what you put in and it's still not correct, you must have made a mistake somewhere. Go back to your work and try to find it. It is very difficult to find your own error. Here's a technique that might work for you. If you can't find the error within 10 minutes, stop, go take a break for 5 minutes, come back and on a fresh sheet of paper, without looking at what you did before, rework the problem. Another thing that really works well is to actually say the steps out loud. If you say them in your head, it's not as effective. The mistake you made the first time, you'll tend to make again in your head. But if you say it out loud, you tend to catch the mistake. There's something about saying it and hearing it that triggers the brain to notice that it's an error. My dog gets lots of problems explained to him. So don't worry if there's no one there and you feel like you're talking to yourself. That's kind of the stereotype of the scientist anyway. We talk to ourselves a lot. Why? Because it works. Okay, let's take a look now at the next problem. This next problem is very similar to the previous problem, so I'll leave it to you to do at home. On the next problem, we have a slightly different thing that we're supposed to do. It wants us to find the largest domain for the function f of x equal x minus 1 quantity squared with upper x bound of 6, such that the function is 1-to-1 and non-decreasing. Well, first off, I read it, but there were so many words, I kind of got lost in the whole thing. So let's go back to the beginning. Find the largest domain. That's all the things that x can be. For the function x minus 1 quantity squared. We've already covered quadratic equations. Let's go ahead and put the graph of this on here. Remember that this is the graph of the toolkit function y equal x squared that has been transformed and shifted. Now we have x minus 1 quantity squared. Because the minus 1 is inside the parentheses and subtracted from x, that's a shift left or right. X things do the opposite of what we expect. So a -1 must move it to the right one. Otherwise, it's the same toolkit function. When we graph this, then it's got shifted to the right one. So 0, 0 has become 1, 0. 1, 1 has become 2, 1. And 2, 4 has become 3, 4. That means that -1, 1 has become 0, 1. And -2, 4 has become -1, 4. Each point got shifted to the side by 1. Here's our function. Well, it's true. Looking at this function, I can see it will not pass the horizontal line test. That means the inverse will not be a function. But coming down here, it wants me to find a one-to-one domain. In other words, find a section of the original function that is one-to-one, okay, with an upper x bound of 6. An upper x bound, well, 6 would be over here somewhere. Okay, well, how far could I go on the graph until it started to repeat y values? Basically, down to the vertex. So I can use a restricted domain. They indicated that they want it to end at 6 on the right. Upper x bound, that means the right bound is 6. The lower bound can go until the y values begin to repeat, which is at the vertex. So what's the x coordinate of the new vertex? 1. My restricted domain would go from 1 to 6. That would give me a one-to-one section that I'm going to highlight in yellow. Do you see how the yellow part passes the vertical line test and also would pass a horizontal line test? By restricting the domain to this region, I can create a graph that is a one-to-one function. Let's enter the domain and see what it thinks of our solution. Notice that I use square brackets since I'm using both ends. We'll see what WebWork thinks of that. I did produce a one-to-one section, and non-decreasing means it's not going downhill from the left to the right. I forgot to check that piece, so let's check it now. As you move from the left to the right on the graph, it decreases here, so I don't want that portion. But I do want the portion where it's not decreasing, which is the portion that I've highlighted. It looks like 1/6 will work. It's correct. Now, what about the rest of the problem? The rest of the problem says find the inverse of f restricted to that domain. What does that mean? Well, let's think about what's happening. I don't have it on the graph, but let's go ahead and plot what the point at 6 would be, keeping in mind that it's way up there. So we'll put a dot, 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 and then we'll put a point. It would connect at 6, 36. In other words, I have the ordered pair 1, 0 and the ordered pair 6, 36. What do you think is going to happen when I swap my x and y? Yes, I also swap domain and range. Domain is the things that x can be. Y is the things, or range is the thing that y can be. So I'm swapping domain and range when I swap x and y. And that means my new domain of the inverse will go from 0 to 36. Let's find the inverse now. Remember that step 1 is to replace the f of x notation with y. This gives us y equals the quantity x minus 1 squared. This is ideal for solving with the square root property. But first, we need to swap the x and y variables. So we swap x and y, and we label it inverse so that we don't get nervous on the test and accidentally swap back again. You think that wouldn't happen to you, but it does happen every semester to somebody if they don't label. Please, please label. It gives me a chuckle, but it doesn't do anything for your grade. Okay, when we get to here, what do we do next? Well, I've restricted this to a one-to-one section, so I know the inverse will also be a function. The yellow portion does pass the horizontal line test. I need to solve for y. Then I can apply the square root property. These notations out to the right are exactly what I'm expecting to see on your exams and also on the write-ups you do for the discussion forum. I found in past semesters that when I ask students to write a simple explanation out to the right, they don't make as many mistakes. And I'm not talking about a few less, I'm talking about a lot less. It really helps students to write down the reason for each step. So please do that on your exams and the write-ups for the discussion forum. This is going to give me, well, on the side without the square, a plus or minus. On the side with the square, I just get the radical. That's the rule for the square root property. When I take the square root of the square, it lifts off the square and I'm left with y minus 1. However, remember that we restricted the domain and we're going to have this be between 0 and 36. The old y values become the new x values, and the old x values become the new y values. So y has to be between 1 and 6. Let's see what this does to that plus or minus. The next thing we're going to do is add the 1 to isolate the y. But don't forget about these restrictions that we're carrying along because of the restricted domain. Remember, we took the two ordered pairs at either end of the domain and we swapped the x and the y. X was going from 1 to 6. So now y is going from 1 to 6. Y was going from 0 to 36. So now in the inverse, x is going from 0 to 36. When we isolate y, we add 1 to both sides of the equation. When we write 1 plus or minus the square root of x, what do you think we're going to have to do to force y to be either 1 up to 6? You're right, I can't subtract. If I subtract anything from this, it becomes less than 1. So I have to eliminate the negative square root. Because of the restriction on y, that it be 1 or bigger, I can't subtract a number from 1. I can only add. This means that my restricted domain gives me the inverse function of 1 plus x. And this carries the restriction that y is in 1 to 6. Now, this also carries the restriction that x is in 0 to 36. Most of the time, we restrict the domain. So most of the time, we would write the following: y equal 1 plus square root of x, x in 0 to 36. Then we know that we've got the right equation. Let's plug that in and see what we get. This is going to be 1 plus the square root of x. Remember to put parentheses around the radicand, the expression that is under the symbol. 1 plus square root x. Now we'll check our answer. Bingo, we got it right. I know this is a little tricky and a little bit hard, so be very careful and take time to write your reasons out to the right side. Also remember that when you're swapping the variables, you're swapping the domain and the range. The next problem is very similar to the previous problem, so I'll leave it to you to work it out. This time, the function is x squared minus 5, which means that it's been pulled down 5 instead of being shifted left or right. They want an upper bound x of 8, which means that on the right side, your domain will stop at 8. You need to find out where to stop on the left side by looking at where the vertex is. Then you can form a restricted domain where the function is one-to-one and non-decreasing. You'll also want to take care when you're looking for the inverse function by remembering that the restriction on the domain and range will probably eliminate one of your possible answers. Let's take a look now at these graphs. I'm not real sure what's going on with these graphs down here. You can't hardly see the graph. I'm hoping when I click on them, they get bigger. It wants to know which graph below is not one-to-one. All slanted lines are one-to-one, so I know that one's okay. This looks like a cubic. If I blow it up, well, it doesn't really help much, does it? It's the same picture. But it is one-to-one because it passes the horizontal line test and it passes the vertical line test. Cubics that don't have a wiggle tend to be one-to-one. This one, on the other hand, is, well, I've only got a little section of it. It's almost like the tail, and I can't see the whole picture. But based on what I can see, it does pass the vertical line test, so it's a function, and it passes the horizontal line test, so it is a one-to-one function. So far, I don't have one that I think doesn't pass until I click on D. It does pass, again, what little bit I can see, it does pass the vertical line test, but it does not pass the horizontal line test. I have the same Y value in two places. That means the Y value gets used twice, which means when I swap X and Y, the X will get used twice. And that would mean the inverse is not a function. D is not one-to-one. I'll leave it to you to do the next problem, but you can tell it's rather similar to the previous ones. And I'm sorry they're so skewed and off the page. I don't know what's going on there. Let's take a look at the next problem. This is problem number 8. Let the graph of f of x be given below. The graph of f of x looks like a negatively sloped line. It is a slanted line, which I know means that it is a one-to-one function. So the inverse is also a function. Find the following. Find f of 0, then find f inverse of 0. What does that mean? F of 0 and f inverse of 0. Well, let's write down what little information we have so far. On problem number 8, I'm looking for f of 0. Remember, this means find y when x equals 0 on graph f. Okay, well, this is the graph of f. So I go to 0 on the graph and I drop down until I reach the graph and I have the intersection right here at -1, -2, -3, -4. Let's take the picture and let's label it so that we have a little bit more to work with. I'm going to take a picture now. Looking at the picture of the graph, I want to blow it up a little bit. One thing, it's kind of hard to see. This point right here would be the point 0, -4. That means when x is 0, the y value is -4. I can then say that f of 0 is -4. What about f inverse of 0? What does that mean? I found f of 0 equal to -4 by looking at the graph of f. Unfortunately, when we write this, we mean find y again when x is 0 on the graph of f inverse. I don't have the graph of f inverse, and that's a problem. But I can apply what I've learned about swapping x and y and swapping the domain and range to figure it out without having to find f inverse of x. Finding y when x is 0 on the graph of the inverse is the same thing as find x when y equals 0 on the graph of the inverse, which is the function. Remember that they're inverses of each other. It works in both directions. So if I want to know what the y value is on the inverse when x is 0, I can find the x value when y is 0 on the graph of f, which is what I have here. So now I need to find a y value of 0. Remember, y equals 0 is on the x-axis. That would be this point right here. This point is -2, 0. On the inverse, that would graph as 0, -2. Let me graph the inverse function for you. The inverse of the point 0, -4 would be -4, 0 over here. Since the inverse of a slanted line is another slanted line, I can connect these 2 points that are on the inverse function. Now, I need to find the identity function to determine whether or not they're truly inverses. Remember that the identity function goes through the origin at a slope of 1. It cuts quadrants 1 and 3 in half. I'm going to draw it with a dashed line, hopefully, provided my index card doesn't slide out from my fingers. Do those look like they're mirror images of each other? Well, yeah, they pretty much do. Given that I was drawing it by hand, this is pretty good. This portion lays on this pink portion. This pink portion lays on this blue portion. When they fold together, they'll line up. They are inverses of each other. So we need to find x when y is 0 on the graph of f of x. So remember, the graph of f of x was the first one we graphed, which was the original blue line. The inverse is the pink line. Notice that when we're on f of x, we want to find the x value when y is 0, and that gives us -2. That means that f inverse of 0 on the other one is going to give us -2. Notice on the inverse function that when x is 0, the y coordinate is -2. This gives you a way of finding it without actually having to graph it or find the other equation. You didn't need to graph the inverse to know that. This gives me -2 for the second solution. On this graph, it wants us to find the inverse function's graph. Let's think about what that might do to the graph. And again, let's take a picture of it so that we can draw directly on it and see what it would look like. I found over the years that I'm not terribly good at this, so I've had to practice this quite a bit. It's not something I'm instinctively good at. You don't have to be. You can learn to do it like I did. This is problem number 9. When we look at problem number 9, I'm going to paste the picture of the original function here. When I look at the original function, the directions are to find the graph of the inverse function. Remember that it will be a mirror image across the identity function. Take your index card or your credit card or your ID and draw the identity function, y equal x. I'm going to draw it again with a dashed line so that I know which one is the identity function. That's pretty good. Now, I need something that forms a mirror image of that across it. Imagine painting this with blue paint and then producing a mirror image on the other side. Let's draw the mirror image in gold. I think my gold is too large. Let's start with a smaller gold. It starts at the origin, and then it's going to make a mirror image like that. Notice that when it reaches the identity function, both points should coincide and be on the identity function. They always meet on the identity function. And then what would this look like? Well, it starts close, and then it kind of goes away from it. Like that. Okay, well, what am I looking at here? This could be maybe a square root function, the upper arm of a right opening parabola, and this could be the right arm of an upward opening parabola. I know those two are inverse functions of each other, so I think I've probably got a pretty good idea of what it looks like. Coming over here to the graph, it's clear that this one is wrong and this one is wrong. That gives me two possibilities. Now I need to check by looking at ordered pairs. Remember when you're doing this, that if you take the ordered pairs, you should be able to swap the coordinates to get the point on the inverse. If I swap 0, 0, I still have 0, 0, so it's on both. If I swap 1, 1, again, I get 1, 1, so it's on both. Looking at the original blue one, though, I can see that it also has this point here, which is at right 4 up 2. So I should have 2, 4 on the graph. It looks like my second portion is a little bit off. Let's graph the second portion again and put it at 2, 4, which would be here. Now we can come over to the two graphs that are possibilities and see which one goes through 2, 4. This one definitely does go through the point 2, 4, but this one does not. That means A must be the inverse function. Now let's look at this function right here and repeat the process. When we repeat the process, we're first going to take a picture of the function so that we can draw the image ourselves. That makes it a lot easier to do. Blowing the picture up a little bit so that I can read it better. I've got, well, part of a line segment. Okay, it's going to form a mirror image across the identity function. So let's take our index card and put that on here. We'll do the identity function with a dashed line again so that it looks different from the other two. There's my identity function. That line looks parallel to me. Parallel. Well, if it's parallel, then the mirror image of it would be parallel too. Let's check if it really is parallel. It goes through this corner exactly and this corner exactly, which means it goes right 1 up 1. Then it does right 1 up 1, right 1 up 1, right 1 up 1. It is parallel to the identity function, which also has slope of +1. Where would the mirror image of it be? Let's take a couple ordered pairs and write them out. This ordered pair is -1, 1. This ordered pair is 0, 2. This ordered pair is 1, 3. And the last one I can see for sure is 2, 4. Now let's produce the mirror image, and we'll do it in pink by swapping the coordinates of each ordered pair. Instead of -1, 1, I'll have 1, -1, right 1, down 1. Instead of 0, 2, I'll have 2, 0, right 2, don't go up or down. Instead of 1, 3, I have 3, 1, right 3, up 1. Instead of 2, 4, we have 4, 2. Right 4, up 2. Now connect those dots with a line and see if that looks correct to you. See if it looks like it's the mirror image of the blue line across the identity function. Yeah, given that I hand drew it, it looks pretty good. I think those would match up. So that's what we're looking for over here. We're looking for something with slope of 1 that goes through these ordered pairs. This one does not go through the point 1, -1, or does it? Let's check the scale because I think the scale is different. The scale is different. I think that says 9. Is that really a 9? No, it's a Y. Good heavens, I need new glasses. Looking at this, it does not go through the ordered pair 1, -1, so that can't be correct. Let's look at graph B. It also, well, wait a minute. It does go through 1, -1, and 2, 0, and 3, 1, and 4, 2. It looks like B may be the solution. Let's verify that C and D can't be correct. Well, clearly C is wrong. It's a downhill line. Let's look at D. D does go through 1, 1, and it also goes through 2, 0, 3, 1, and 4, 2. Which one is it? Let's go back to our original and see where it actually started. It started here at -1, 1 and had no bit extending past it. This one does connect at 1, -1, but it has a little bit past that is not present in the original function. Therefore, B is not correct. The answer is D. Always make sure when you're doing multiple choice that you check all the possible solutions. One may be a better choice than another. That means that our answer should be D. Now we'll check our answers and we're correct. Now let's talk about doing it on a table. When we're doing it on a table, remember that we swap the X and Y values, swapping domain and range, and swapping the coordinates of each ordered pair. F of 8 means go to the function named f, which is given here in row 2. Let X be 8 and find the Y value. Go to the X row, find 8, drop down to the Y value, and you get 8. F of 4 means let X be 4 and find the Y value on F again. Come up here to the X row, find the 4, then drop down to the Y value on F of X and also get 4. What does this mean? F inverse of -9. This means that this is the X coordinate on the inverse, which must mean it is the, Y coordinate on the function. Let's find the Y coordinate on the function with -9. It's looking for the Y value on the inverse, which is the X value on the original function, which gives us a 1. Now let's look at F inverse of -10. Again, this is the X value on the inverse, which is the Y value on F. Find -10, which is here. Now find the X value that goes with it, 6, which becomes the Y value for the inverse. And check your answers. Let's take a look at the next problem. In this problem, we're to convert from x degrees Celsius to y degrees Fahrenheit using the formula f of x equals 9/5 x plus 32. The right side is simply a slanted line with slope 9/5 and y-intercept of 32, the b. This is a function since all slanted lines are functions. They're also one-to-one functions, meaning they pass the horizontal line test. It wants you to find the inverse function. It says if it exists, but we know it exists because it is a slanted line. That means that you're going to rewrite this, replacing the notation with y, then labeling it the inverse and swapping the x and y variables, then solving for y again. Finally, because it is one-to-one, you'll replace the y with f inverse of x. I'll leave it to you to work out the details. Let's take a look now at a question about some notation. This says, let f of x equal -5x minus 2. Find and enter the inverse of f of x. It is a slanted line, so we know the inverse will be a function. We're not sure what it wants in this particular line. Does it just want the right side? Does it want y equals? Does it want f inverse equals? I'm really not sure. I'm going to enter it with y equals and see what it does. First, I need to find the inverse. I have the original function as -5x minus 2. I'm going to replace f inverse with y. F of x rather, with y. That gives me y equal -5x minus 2. Now I'm going to label it the inverse and swap my x and y variables. That gives me x equal -5y minus 2. I know that it's one-to-one because it's a slanted line. How do I know it's a slanted line? I recognize that this is slope-intercept form, with the slope being -5 and the y-intercept being -2. The only two lines you really have to worry about are the horizontal line and the vertical line. Obviously, neither one of them is one-to-one, but they are inverse equations of each other. Now I know it's one-to-one, so I'm going to solve for y. First, I'm going to isolate the y term. To isolate the y term, I move the 2 to the left by adding 2. This gives me x plus 2 equal -5y. Next, I'm going to isolate y by dividing by -5. This gives me y equal x plus 2 divided by -5. Now, I happen to know that it is a function, which means I can use inverse function notation. Since the name of the original was f, I'll call this f inverse of x. Let's see what it's looking for in this blank. It may or may not want the y equals. It's not clear. Sometimes it won't be. We'll just try it and see. We're looking for x plus 2 divided by -5, but it's the whole x plus 2, so I need to put it in parentheses. I can also put the -5 in parentheses, but probably it would take it without it. Let's check our answer and see if it likes the form I answered it in. Nope, it does not want the variable y. I'm guessing that it doesn't want anything and just wants the right side. Let's try that and see if that works. That's what it's looking for. Now it wants to know the correct notation for the inverse of f of x. I know it is a function because it was a slanted line originally, and those are always one-to-one. So the correct notation is f inverse of x. Now let's check. 2 green checks. This problem here involves finding the inverse of a square root. These are among the more difficult ones, so let's take a look at it here. Notice that the inverse is going to carry a restriction on the domain because what's under the radical cannot be negative. That will create a restriction when we go into the inverse. First, we need to determine if this is actually going to be a one-to-one function. Let's write down what the graph of this would look like. Remember that when we have an equation, we can build it on a toolkit function, such as the square root of x. When we do that, however, remember that it gets transformed, and if it's multiplied by x, it has to be factored off before we can determine how much it got moved left or right. That makes the number inside the parentheses -8 divided by 9. Since if we distributed it back out, we would get 9x minus 8. This tells me here that it has been either stretched or compressed horizontally. Since it does the opposite to what I expect, this is a horizontal compression by a factor of 9. Then what's on the inside tells me it's moved left or right because it is subtracted from x. Because it's inside the operation, the square root, it does the opposite to what I expect, and it moves it to the right 8/9. Now, what does this do to the graph? Think about your graphs on the toolkit function. The normal square root has these points: 0, 0, 1, 1, and 4, 2. If we shift everything to the right, it gets shifted 8/9 to the right, but then it gets compressed, which means we're dividing each x coordinate by 9. It's going to end up looking something like this, where it got compressed horizontally and it got shifted to the right where 8/9 is. It still passes the vertical line test and the horizontal line test. That means that it is a one-to-one function. That means we should be able to find the inverse function. Now we're going to write the equation down and solve for the inverse. First, we replace the function notation f of x with y. Next, we swap the variables and we label it the inverse. We know that it's 1-to-1, so we'll go ahead and solve for y. That's because it passed the horizontal line test on the original function. Now we can solve for y by first squaring both sides to lift off the radical. This is basically using the square of both sides, but it's a risky thing to do because when you square sides, you can introduce false solutions. It lifts off the radical on the right, and this will give us instead 9y minus 8 equal x squared. Remember, though, that this originally had some restrictions on the x value because the value underneath the radical can't be negative. Those values will carry over into restrictions on the y value over here. Because we know it's 1-to-1, we'll go ahead and solve for y. Solving for y means isolate the y term. That means adding 8 to both sides of the equation to lead to x squared plus 8 equal to 9y. The next thing to do is to isolate y by dividing every term on both sides by the 9, or dividing both sides by the 9. You can do it either way. Or you could have y equals x squared divided by 9 plus 8 divided by 9. We know it is a function, so we can use inverse function notation. Notice that this one didn't have a plus or minus. There was nothing to eliminate from the possibilities. We didn't have to think about the restrictions, but it does carry restrictions. If we think about the original graph, let's come back to here. What's the domain of this original graph? Well, it goes from 8/9 to the right. So the domain of the original is 8/9 to infinity. What is the range of the original? What y values are we using here? Well, it starts here on the axis, so 0, and then all the positive values. Remember to pull the values back and cover up the y-axis. This is the range 0 to infinity. When we swap the variables, we swap domain and range. So we're saying that the range of the original is the new domain of the inverse function. So we have this restriction that x must be in 0 to infinity. We usually do list the restriction on x to be sure that people know it's not the full graph, just this part of it. Now we'll put in the restriction, or rather we'll put in the function. I'll probably put in the x squared plus 8, all divided by 9. It didn't leave me a place for the restriction, so I'm going to guess it's simply looking for the equation part, and I'm going to check my answer. That's what it wanted, but keep in mind that there is a restriction on it because of the restriction on the original function. You're swapping domain and range. The last problem is somewhat similar to the previous problem, so I'll leave it to you to figure this one out. You may have to square two sides of an equation in order to get rid of this one, which may mean that you have a longer process, but the process is the same as on the previous problem. I hope this helps to explain what inverses are and how you can find them algebraically, how you can find them graphically, and how you can find them by swapping the points on an ordered pair. After this, we'll be moving on into the next chapter we cover, which is chapter 5.